All right, so good afternoon. So it's true that this is the 2 o'clock slot, but this is very much sort of in the spirit of what the 11 a.m. talks have been. It's not going to be as formal and hopefully some discussion. So I'm going to talk a bit about, I think, what can fairly be called the standard model of AGN feedback in simulations and what the implications of that are, and then about something I've been cooking up, which I think will I don't know, is in some sense better. So let's see. So the standard model of AGN feedback is this thing where you have it's the minimum of m dot Bondi, g squared m squared. Is this big enough? It's been a while since okay. There's 2 there, rho over c cubed. This is a sound speed. So you take the minimum of m dot Bondi, m dot Eddington, g, m, let's see, the c is here, there's a kappa, and there's a radiative efficiency if I'm doing m dot. And then it's local thermal feedback. So thermal meaning basically that E dot is equal to epsilon m, so this is epsilon r, epsilon m, m dot c squared, where this is 5 by 10 to the minus 3, this famous value. P dot is equal to 0, and m dot out is equal to 0. Is this me? So right. So I got a prepaid number, and apparently the person who had my number immediately before gets debt collection calls like 3 times a day. So okay, so local thermal feedback. Local meaning basically the energy is injected in a resolution element. Thermal meaning that you're injecting no momentum, only thermal energy. So you change the thermal energy of the particles without changing their kinetic energy, and that's it. Yes. The third one is m dot outflow, so I'm just sort of including this for completeness. You could imagine driving a wind and returning some of the gas to the simulation, but this is, for this case, is defined to be 0.
But that wouldn't be consistent with P dot equals 0, right? One leads to the other.
That's right. Yeah. I mean, you could inject the mass with 0 momentum. So I guess m dot doesn't lead to p dot, but p dot equals 0 implies m dot equals 0. That's true. Okay, so this, like I said, I think can sort of fairly be called the standard model. There are other people now, a lot of time has passed since this was published. A lot of people are doing things that are more sophisticated, in particular the simulations that, there are many groups, but of course, this being my talk, I will highlight the simulations that I've been doing, where we're sort of trying to track, gas flows from sort of kiloparsec scales to parsec scales, including a lot of both radiative and kinetic feedback channels. So we're really, trying to sort of, take the world beyond this. One of the things which is coming out of this is a project that we have been working on here that Fabrice and Arif Babul we've been working on for, I guess, about a year now, where the idea is to take these higher resolution simulations and extract the actual m dot. So in other words, if you take the information that you have in a lower resolution, for example, cosmological simulations, you might have gas densities at kiloparsec or 100 parsec scales, maybe 10 parsec scales. If you take the information that you have at larger length scales, so we propose to take these high resolution simulations and extract a model where if you put in the smooth gas density at 1 kiloparsec, it will tell you what the accretion rate is at 1 parsec. So we're trying to sort of bridge this gap. So those are just 2 bits of advertisement. But now let's return to this. So there are 2 interesting questions, I think, whenever you're thinking about this stuff. The first one is, what does physics do? That is definitely an interesting question. That's what you would like to come as close as you can to modeling. But the other question, and it's distinct, is what does my numerical method do as I change parameters like, for instance, the resolution? So in other words, what are the implications of the numerical model that I've cooked up? So that's what we're going to explore for a moment here. So the first thing is, okay, let's ask, what happens if you, for example, change the resolution? So let's look at heating and cooling rates. So the cooling rate is the usual n squared. Sorry about this, because I'm out of practice with chalk here. N squared lambda of t, and then you have a heating rate, which we've already written down, but this is E dot, not the volumetric heating rate, so we need to put the volume back in. So this is epsilon m dot c squared 4/3 pi r cubed. So this is the radius over which you're injecting the energy. So in the sort of definition of the standard model, this is the resolution of the simulation. But let's ask, okay, what happens as a function of radius? So this is dE, dV, dt. So this one is easy. We want to know what goes on with radius. All of these things are radius independent except for the radius, which is there explicitly. So this goes as -3. So the interesting bit comes whenever you think of what happens with the cooling rate. So here, there's some radius dependence hidden in the density. So if you sample smaller and smaller length scales or run higher and higher resolution simulations, then you'll resolve higher and higher density peaks. So we need to make some assumption about this. Assumption that we'll make is the sort of favorite one, which is that it's a power law. So there's some scale density, and then we have r over r naught to some power minus alpha. And we'll consider a couple different values of alpha. So once you do this, the cooling rate is proportional to r to the -2 alpha. So there are two interesting cases. So first of all, let's consider the steep case, so alpha large. So if that's the case, then this goes as a large negative power of r. So this is the steep density case, steep density. And then the other one is the shallow density case, where alpha is a small number. So this goes as some flatter function of r. So this is the shallow.
Wouldn't the temperature also have fluctuation? Can it have local fluctuation with r dependent?
That's true. Definitely true. So this, I mean, what I'm going to do here, I'm basically going to assume that things are isothermal. So that'll change the details of the argument, but I don't think that it'll change the sort of overall conclusion. So to keep things simple for the time being, I'm just going to say that it's isothermal. So what do we know so far? Well, as we inject for example, the heating energy in smaller and smaller radii, if the density is steep, then eventually you get within a certain radius and cooling wins. So this makes sense. Cooling has a strong dependence on density. If the density is steep, eventually cooling wins. So what does that mean for feedback? So I'm down here for the steep density case. As I go to small radius, cooling wins, then that means that feedback is ineffective. So in other words, I inject a bunch of energy, but the density is so high that I can efficiently radiate that energy away, and the black hole sort of doesn't know that I injected the energy. So feedback is ineffective in that case. The other case is the opposite. Shallow density, in this case, feedback is effective. So if I go to small enough radius, there's always some little sphere, which is small enough that when I dump the energy in, it exceeds the cooling rate, heats the gas, the black hole cuts off its own accretion, and feedback is effective. So okay, this is pretty simple so far. Everything is pretty clear. But then an interesting thing happens whenever you ask yourself, well, we've considered this as a function of radius, but that's not what you actually do. So what we've imagined here is running different simulations at different resolutions and ask, okay, does heating or cooling win as you go to high resolution simulations? What you actually do is fix the resolution and then allow black holes to grow in the simulation. So next, let's consider that case. Yes.
This radius is from the black hole, and the resolution here is you're looking at the innermost resolution element, whatever size it is, that contains the black hole.
That's right.
So even if you cool there, and the other stuff outside cannot cool, then you will accrete whatever was in that innermost region, but you do not necessarily set up a high mass flux further out. So maybe it's just a transient cooling event, then the black hole establishes a standstill with the environment, albeit at a larger radius. So
that's true. So what you're arguing for is sort of like supply limited accretion, and that will happen. I mean, that's definitely, in that case, that would happen if you're limited by the cooling of the gas at larger radius. But the important thing about that is the black hole has nothing to do with it. The black hole is not regulating its own growth if that's what's happening. So it tries to inject the energy, it fails because there's this little cooling sphere. And then it just eats as much as it can and then stops. So in other words,
there's a low density bubble around the black hole, and whatever energy output it has will affect the region further out.
Well, that's right. So you have if the black hole eats that gas, you have a little bubble of vacuum. So it will sort of encourage a bit of inflow. But the important thing, I think, for the moment is that m dot in that case is regulated by the characteristics of the galaxy mostly. Whereas what we're asking here, what I mean to ask here, I haven't quite gotten to it yet, is the black hole capable of regulating its own growth? So in other words, is the black hole a player in feedback or not? So in the situation that you describe, I think, I mean, it's true that m dot will go down, but it's not that the black hole, I mean, the black hole is trying but failing to limit its own growth in that case. It has to do with the galaxy, not the black hole.
No? The regions outside, the regions that cannot supply fast enough, or cannot do it because they're heated only.
Heated by what? Wait, heated by what?
The black hole is basically emitting energy, and this energy has
Yeah.
it simply heats.
No, so
further out.
Okay, so here I think I misunderstood what you were asking. I think what you're imagining is something like this. I have the black hole. Maybe I'm wrong, but I have one resolution element around the black hole. So in this model, the definition is that it injects all of its thermal energy into that resolution element. So if it can't effectively heat that resolution element, it can't effectively heat the next one either. If you imagine I have some distribution of heating that includes a lot of resolution elements, then we're on board. Then I agree.
But if we just take what you suggested, one step of realism further. So suppose it cools efficiently. There is no pressure support for this mass. The black hole accretes it.
Yes.
What would physically happen? Not just in the terms of this kind of simplified problem. What would happen would you would have a low density environment, a hot thin bubble around the black hole.
But it's not hot. It's not hot.
No,
we said that it's cooling efficiently.
After you accrete, the density falls. It becomes thin and hot. And now the hydrostatic support is ranges further out. So I don't see why this leads to a conclusion that the physical system would be one that the black hole will now basically have to accrete whatever the galaxy is supplying it, at the rate that the galaxy is supplying it.
So I think, I mean, where I'm disagreeing with you is if you say cooling is efficient and the gas is not hot. I bring the density down, but it stays the same low temperature. There's nothing to heat it. Cooling is effective. You're saying, sorry, so you're saying the cooling rate goes down because okay, it didn't fill in that step of the argument. That's right. So, okay, so then if I want to, let's see. So, I mean, so what really happens is an interesting question, maybe a difficult one, but if we have density versus radius, then what you're saying is, okay, you form something like this. So then I would argue, yeah.
Then it would not be correct to interpret this result as meaning that the black hole is not a player in the regulation.
Okay, that's true. So I guess, I mean, the argument that I would like to make for the present purpose is that you have a low pressure region here. Well, if you heat it up, then maybe it's in pressure balance. But what I would like to have happen is for this to refill the power law that we assumed at the beginning here. So the gas outside would flow in a little bit and reform the power law. Yeah, that's true. That's true. That's fair. That's true. Okay. Good. So thinking about what happens as a function of mass. So we can do something here. So there's one quantity which we would like to, which is interesting, I'd like to think a little bit about, which is the radius where heating equals cooling. So let's just write that down. So we have n naught squared r over r naught minus 2 alpha lambda that I'll carry around, and then heating m dot c squared 4/3 pi r cubed. So we need an m dot here. So the only thing that we're going to end up needing is that m dot goes as a positive power of m. So you can plug in either the Bondi rate or the Eddington rate, but I'm just going to plug in the Eddington rate for present purpose. So we have 4 pi g m opacity kappa epsilon r. So this is what we want. Our r's are there. So we r naught cubed, and then we bring this over here. So there's a 3. This goes away. And then these guys come over. So we've got lambda n naught squared. Okay, so now this, let's see. No, I don't want to rewrite this. I've crashed into my other formulas a little bit. But the only thing we need is this power. So this is 1 over 3 minus 2 alpha. One point that I wanted to make over here. We had the steep case and the shallow case, so it's a number that I want you to have in your head is when those two things balance. So the crossover point between those two. So that happens whenever minus 2 alpha is equal to 3. In other words, alpha is equal to 3 halves. Sorry, minus 3. We'll need that number again in a second. So I've solved for, okay, the radius in terms of the scale radius R0, which just defines the density, at which heating and cooling is equal. So now here's our M. All of these things, okay, this is a parameter of the simulation, let's say. Physical constants. The only thing, okay, opacity, physical constant. So there's some efficiencies. But the main thing that we want here is M. So we want to know how this behaves as a function of M. So let's consider first the steep case. So in that case, alpha is large. This is negative. This goes as a negative power. So this goes as some negative power.
Sorry, the M sigma would imply a connection between n naught and m between the density and the normalization of the density and mass.
That's true. That's operating on some kind of global galactic scale, which is not necessarily the sort of parsec scales right around the black hole where we'd like to actually set the density.
How would you set it then? I mean, probably you would want to set it that at the radius of influence it merges with some density.
Yeah, that's true. So at the moment, okay, so let's try. Let's step back into the not what would physics do, but what are the implications of the way that we've numerically implemented this? So considering the steep case, alpha is large, so that makes this negative. So this goes as a negative power. There's our m. So the radius at which heating and cooling is equal goes as some negative power of m. So it looks like this. So we have m, and then we have r over r naught, and I'll put sub equal. So this is the radius where heating and cooling is equal. This is the steep case. We know for that case, whenever you're below this radius, cooling wins. Whenever you're above this radius, heating wins. Now, what is the resolution of the simulation, and what role does this play? So I'll make this. I'll make a line here, which is supposedly the resolution of the simulation. This is r resolution over r naught, and this is just a constant. Okay. So now, what happens? What are the dynamics of this simulation? I start off black holes with some mass, and then they grow. So I'm always, by definition of the model, injecting the thermal energy at this at the resolution scale. So mass is going up and up and up. Cooling is always winning. Feedback is always ineffective. And I suddenly get to this crossover point where what has happened is the little cooling sphere around the black hole that I argued before has become unresolved by the simulation. So it's not physics that's going on here. It's finite resolution of the simulation. So now at this point, feedback becomes effective. So here I have self-regulation. Here I have free growth. Okay, but we had one other case. So there are two sign flips here, which happen to give you the, at least it was to me, I think, interesting result. Let's see, how do I want to do this? Let's move fully onto one blackboard here and just run through the same argument again for the other case. So we have m, we have r over r naught, we have resolution. Okay, now, shallow case. Alpha is small. This is a positive power of m. So this goes as a positive power of m. But the other sign flip, which is helping us out here, is we know that for the shallow density case, for small radii, heating wins. For large radii, cooling wins. So that's to say, now let's ask just exactly the same thing we did before. You start at low mass, inject at the simulation resolution. Here, you're in the case of the regime where cooling is winning, feedback is ineffective. Eventually, you hit this crossover point where now what's happening is you're suddenly resolving this little heating radius around the black hole. So again, what's going on here is just something which you were previously not resolving is now becoming resolved. And you suddenly find that feedback is effective. So there's this crossover. So you again have, over here you have growth, and over here you have self-regulation. So you can write down these estimates, you can plug in numbers for these things, you can plug in resolution for the simulations that people have done, and I claim, I've done this exercise, I claim that the black hole masses that people publish coming out of cosmological simulations based on this model can be basically fully understood in terms of this crossover point. So that's to say, at least the way I would characterize it is, maybe other people put it differently, but my impression is that the claim that you put this model into a black hole, into a cosmological simulation and follow black hole evolution, and then you find that black holes sort of self-regulate their growth at a certain mass scale is claimed as a success of the model. But I would say it's more like it's sort of baked into the model. So it's more like an assumption of the model. So
it's the result that you have a lot of early growth and eventually they become relevant. You're saying it's purely this resolution.
That's right. That's right.
And it's even more complicated, right? Because people run with different varying softening lengths that vary with time, and that length scale itself is actually evolving, which would be plugging in.
That's true. That's true. I mean, you would assume that at the sort of highest density peaks, it tends to be the smoothing lengths would tend to be the smallest allowed. So, I mean, at least that's what I did when I made these estimates, was to plug in the smallest allowed length scale that they published. But so in principle, hopefully in this 20 minutes, I've saved you from maybe 1,000 AppJ pages. So you can thank me for that later. But okay, so here ends the first part. Yes.
So here you're basically assuming that density so this was then becomes
Right.
density profile is not changing a lot.
Yeah, that's true. That's true. So if I start changing, I mean, okay, one clarification about that. If I start changing, if by changing the density profile you mean changing alpha,
Yes.
then what I claim to have argued here is that it does not matter. That's the point of considering both the steep case and the shallow case.
Alpha
But the,
changes as a function of time and as a function of R as well.
So it's not a parallel sense. It's a
Yeah.
local.
well, that's right. But whatever value it is, the thing is, I mean, alpha doesn't really, well, okay, so it comes into this in the power. But whatever this is, like whatever this combination of physical constants is, okay, I mean, it's true. If I change alpha by a lot, it will change it in this power here. So it could make a difference. If I start changing n naught, then I start changing, then that will also change things. But, so, okay, so that's true. Okay, so let me see how we're doing here. Oh, good, okay, not too bad. Let me see if there's anything else that I wanted to say about this. Okay. So where does this fall down? Because you notice, I mean, this is like, there are caveats, right? I mean, you don't know what alpha is doing as a function of radius. Maybe there's a correlation between m and n naught. I have assumed things about the dynamics. There are definitely caveats. But in general, I mean, I would say this is fairly general. And the only thing I really depended on was that the accretion rate limit went as a positive power of m. So what is sort of wrong with this? Or what would I say that you need to do in order to make this, what I would say, a more physics-based model of feedback? And the key thing, at least my interpretation of the key thing, is where you get into trouble is assuming that you should be injecting energy at the resolution scale of the simulation. In order to sort of complete this as a model, what you need is some argument for why you should be injecting energy at 10 parsecs or 100 parsecs or 1 parsec or whatever. And then you need to run a simulation that's higher resolution than that and actually resolve what's going on. So you can fix this by this thing, which maybe we can still draw some. Oh, yeah, here it was. Where you have the black hole, you have the resolution element, and then you're injecting energy over some rather large radius around the black hole. Then you're not resolution dependent anymore.
But then usually you don't have enough energy to actually heat that thing.
Well, that's true. Okay, so this is actually a nice segue into the next thing that I wanted to talk about. So, okay, any other questions about this stuff? Or? No. Okay.
They always do it when you do star formation and you use some particle algorithms sort of to study present-day star formation. One trick you normally do when you have your resolution element, you look it out at that scale. If I assume the Bondi solution, and even if I'm not resolving the Bondi radius at that point, I can extrapolate the Bondi solution itself. So that can help a little bit, I think, with getting more sense of it.
Yeah. So this is an even better segue into the next thing that I wanted to talk about.
I tried to do that with our simulation. So I assume that density profile is whatever density you have, and calculate the Bondi radius exactly, and the density within that radius. At least in the range of simulations we were looking at, differences were
Okay, so on to the next step. So this grew out of a conversation. So Sarah Markov was visiting IAP, and the conversations with her and Marta. Sarah was really interested in putting jets into simulations. But I was thinking to myself, well, she really wants relativistic jets, so that means very small time steps, and you need to get all the gammas and betas in the right place, and that seems like a lot of work. So I was looking for a way to basically put jets in without doing the actual work of putting them in. So this cooked up this thing, which is what I sort of came up with. So there was this Stinson 06 paper about supernova feedback. So we need a brief digression into supernova feedback as opposed to AGN feedback, which I really like a lot. So the idea is, okay, what's the problem with star formation feedback in simulations? Well, if I have a 100 parsec resolution simulation and I have one supernova go off, then I inject a bunch of energy. But if I inject that energy into 100 parsecs, then what's happening is I'm spreading it over too much mass. So the change in temperature is too low. I don't push myself to this part of the cooling curve where cooling is inefficient and the cooling time scale is long. So then I just radiate that energy away and it has no effect. So the basic problem there is that I'm not resolving what's actually going on, right? What's actually going on is I have a supernova going off in which happens at much less than 100 parsecs, right? It actually is not spread over all the mass within 100 parsecs. It's spread over a much smaller amount of mass, so delta temperature is much higher. Then, thankfully, we have an analytic solution. We have the Settle-Taylor solution, which allows me to track what's going on with that energy before it gets to scales that are relevant for my simulation. So the key thing there is I basically take some of the energy. The fluid equations are conservation equations, right? But I take some of the energy which in principle should be on the grid, on the simulation grid, or in simulation particles or whatever. I say, well, it's in some other state for some amount of time until the blast wave that's generated by the supernova gets to such radius that I can actually resolve it. Once it does that, then I can start saying things like, well, how much thermal energy is left, how much kinetic energy is left, what is the time delay between when the supernova goes off and when it actually injects that energy. So the thing which seems to me to be the sort of key, the key thing about this, which is attractive to me, is the fact that there's an analytic solution which you're using to tell you about time delays, spatial scale, kinetic versus thermal energy, this kind of thing. So what this does for you is if you imagine running higher and higher resolution simulations, then as I double the resolution of the simulation, then the time delay between the supernova exploding and the time when I'm actually injecting the energy into the simulation gets shorter, right? And it does this in a sort of physics-based way. So as I run higher and higher resolution simulations, eventually I'm just going to be, in principle, injecting the energy and simulating the blast wave. So I go from having the blast wave be in basically analytic extra piece, which is tacked onto the simulation, to just directly simulating the blast wave as I scan my resolution to higher and higher values. So this seems to me to be a nice property that we should, we should like to have in numerical simulations. And it seems to me that this will save you from being so resolution dependent, or at least what I argued was so resolution dependent, like the method that we saw before. So that's what I sort of want to do, yes, is figure out a similar model for jets. Go ahead.
I'm a bit confused here. The supernova example, there's a sense in introducing a delay and then introducing the energy and the radius that corresponds to how much in the physical system, because the thing is abrupt. It happens, other stuff is happening in your simulation. You have to time the injection of energy on the right scale at the right time. Mm-hmm. But feedback, for example, can be a very continuous and not very smoothly varying thing. So in principle, the delay doesn't matter, right? If you're talking about, say, an almost steady state, so maybe you have a small problem when the AGN ramps up its luminosity, then maybe you should have introduced a delay and you don't. But if you're looking at the long-term behavior, why should the delay matter, actually? You can still put the energy that you need at the radius of your smallest resolution radius. I don't see what doing the delay would... Unless you're saying that you want to calculate correctly how much energy to put there using a propagation model. Is that the essential piece?
That's the essential piece. Okay, so the delay I just mean to basically illustrate how that helps you be resolution independent. because your sub-resolution model will match onto the simulation. If you fix the resolution of the simulation, then that delay will depend on the resolution, and that will sort of help you continuously match onto some physical solution as you make the higher and higher resolution simulations. You're right, in terms of the effective feedback, that's not the essential thing. With AGN, I think it might actually be more important than it is for star formation.
You vary a lot, and you have to
Right.
time it against some other
Right.
independent process that has a strong time dependence.
That's the thing, right. Because as you feed the black hole, right, if the energy injection is instantaneous, then you have some hope of getting into some sort of equilibrium state. But if you do have a delay between them, then you sort of generate bursty behavior because it can't find the equilibrium, right? So, I mean, I think it has the potential of being important, but it's not the critical thing for the argument that I wanted to make about the sort of, well, yeah, I'll leave it at that. Okay. So the idea here, okay, so design goals. So goals. So one is conserved quantities only. So this, we won't talk much about this conserved VED. Did I get that right? Yeah, okay. So this should be phrased in terms of conserved quantities only. This has to do, I mean, I'll sort of relax that assumption in my discussion now. But in the paper that I've written up about this, this I think is important for how it actually matches, like how you actually put it into the simulations. So in other words, you shouldn't be trying to estimate densities. Everything should be framed in terms of mass or mass enclosed within some sphere or something like this. So it should be simple. Oh, actually, I should say, let's say respect physics. But don't over-elaborate the model. So in other words, it should be things should be very simple. So you could imagine cooking up a sort of MHD equilibrium solution and then trying to do the same game that's done with the blast waves. But I think that would be an over-elaborate model, not justified by what we need for the moment. So the idea is to make things really as simple as possible, bring in as few assumptions as possible. And then as we learn more, whatever, you can make the model more specific. So now, again, I'm going to try to take really the simplest possible case and just sketch what's going on. More elaborate cases are worked out in the paper, but I'll talk about those a bit at the end. So simplest possible model of AGN feedback is that we launch a blob of mass at some velocity, and it has some mass m naught. So the idea here, I mean, what I wanted to change from the supernova blast wave stuff that Stinson already worked out was to have energy going to a small opening angle. So there's some solid angle associated with this omega. Now, like I said, I mean, this is more like this is sort of a simplified case to just sort of sketch out what I want to do. So what will happen here? So to the extent that there's any insight at all here, the key insight is that if this opening angle is very narrow, so how does this differ from a blast wave? Well, if I have some kind of bipolar thing going on where there's a corresponding blob of mass launched on the other side, the early part of a blast wave, the energy conserving phase, pressure forces are accelerating the shock, right? What happens here? I have all this hot shocked gas behind the blob that has flown out. But what are pressure forces going to do? They're not going to accelerate the blob. They're going to tend to accelerate it laterally. So you have up here, this will go into some momentum conserving solution. And for the transverse direction, we're going to need to sort of modify the Sedov-Taylor solution from a point charge to a line charge. So those are the two things that are about to happen. So first, let's think about the long axis. So RL, R sub L for long axis. So initially, before this guy sweeps up an amount of mass comparable to its own mass, then it'll be in a sort of free expansion phase. So you just have the radius of the blob is just equal to the initial velocity times t. So this is at early times. After a while, so at later times, you'll have something that looks more like this. Or we said, okay, pressure forces are not helping accelerate this guy, so it's momentum conserving. So what we have is the initial momentum is m naught v naught is equal to the total mass, which is the initial mass plus the amount of mass swept up. But it's into a small solid angle. So this is, let's see, 1/3 rho omega r cubed, and then this velocity as a function of time that we're after. So this guy, we've already said that this is for late times whenever this guy is larger than this guy, so this we just neglect for a minute. And then we can integrate this differential equation. This is the RDT. So we just solve for this guy and then integrate it, which for the moment, the only thing that I need from this is to say that you have r cubed dr, and there you have a dt. So you get t is proportional to r to the fourth, so r proportional to t to the 1/4. So that's exactly the same as the momentum conserving case that you get in supernova explosions after the cooling time. So this is late times. Okay, so now what to do about the transverse direction? So we need to step back to the good old Sedov-Taylor solution for a second here. So you have this radius of the blast wave. So where does this come from? So this is the thing that we all sort of know and love. So you make this dimensionless. You make the only thing that you can make which has dimensions of a radius, which is this guy. So that's the only thing that we need. We just want to know the sort of size and shape of this region as a function of time, of the region which is affected by this little blob of matter that we sort of shot through the interstellar medium. So this is for the spherical case. So this is just based on dimensional analysis, right? So let's just try to do the same thing. So we'll have Rs for short axis. Now what's happening here? You have a total energy in the explosion, but we'd like something which is sort of asymptotically correct for very narrow opening angles. So this will be a sort of elongated region where, if I'm sort of standing here, then I don't really feel the fact that, there's an end to this line. So the idea is to sort of take that up to infinity and ask, what would a Sedov-Taylor solution look like if we fix not the energy at a point charge, but rather we fix the EDX? So the amount of energy that I inject along a line for an infinitely long line. So if I just do, it turns out, I need the same factors of time and density. The only thing that's changed here is that I have an extra factor of length in the denominator of the scaling quantity. So instead of to the 1/4, instead of to the 1/5, I get to the 1/4. So this then, this is for a point charge, and then I ask, what is the radius of the blast wave? This is our ST. This guy, if I have an infinitely long explosion, and I ask, what is the perpendicular distance that the shock wave reaches, this sort of cylindrical shock wave? Dimensional analysis says that it has to be this. So if I want to know, I should, strictly speaking, write proportional here. Because there's some order unity constant that I would need to actually solve the hydro equations to find. But for the moment, we're just going to forget about in the name of simplicity, I guess we'll forget about the order unity constant. So the key thing for this is the short axis is proportional to, here we have t squared to the 1/4, so it's proportional to t to the 1/2. So now we put this together and see what this looks like. I'm going to do it here, I guess. Here, I'll take away these guys. So what does this say? So here we have time, we have radius. So the long axis at early times goes as t, and at late times goes as t to the 1/4, so it looks something like this. And this guy is always going as t to the 1/2. So it's not as steep as this guy, but steeper than this guy, so it looks like this. So these guys will eventually meet. So what's happened then, because I basically have one fewer dimension to expand the energy into for the sort of line charge case, the time evolution is a little bit steeper. So what has happened is the short axis is caught up to the long axis. So once that happens, I'm back onto the spherical Sedov-Taylor solution. So there will be another kink in the evolution here where this goes to, here is t to the 0.4. So it will be a little bit, steeper than this guy, but shallower than this guy. So it looks kind of like that. So this is 2/5, and this is Sedov-Taylor. So I have this little sort of elongated region. I know, at least in principle, according to a bit of momentum conservation, a bit of energy conservation, and some dimensional analysis, I know what the size and shape of this region is as a function of time. So what I can do is whenever I have a bit of AGN, I want to inject a bit of energy from the AGN, I have some resolution of the simulation. So this is the resolution. I say, draw a line here. I say, okay, well, when this comes on to the simulation grid, when it gets large enough that I can resolve it on the simulation grid, I know this is the resolution. So I wait until the thing is sort of fully resolved by the simulation. So this is now, so I know this time delay. I know how long I should wait. I know how big the thing is. I know its aspect ratio, and I know the balance between kinetic and thermal energy. So that's the idea. So once I've done this, I can play all the same games that you play for the case of set of Taylor blast waves in the supernova case. So you can ask, okay, what if cooling becomes important? So this guy, the short axis, is being driven by pressure forces. So if the densities and temperatures are such that cooling becomes important, then what will happen? I mean, in the spherical case, then you get this transition from energy conserving to momentum conserving. Here you get exactly the same thing. So instead of this continuing to grow and you ending up with a spherical remnant, if cooling becomes important, this will also bend over to 1/4. So this now is Tc for cooling. So you notice, okay, the long axis is going as t to the 1/4, the short axis is going as t to the 1/4. So now it's just sort of a coasting, peanut, if you want. So the point is just that you can play the same games. You can estimate what this cooling time is, and therefore figure out how you should patch this into your larger scale simulation. So. Should I interpret silence as total agreement or total disbelief?
What is a great test problem for this framework?
Yeah, so I did some, what you'd like to do, actually, let me, right, okay, good. In principle, you can just simulate this, right? You can just simulate exactly the situation that I set up and see how close you come. Hopefully, that's not completely wrong. I haven't looked into this in sort of great detail, but I did try to, people do these hydrodynamic simulations of jets, right? So I tried to see if this matches. And at least for the long, it looks, to the extent that I can read off people's, plots of their simulation snapshots, it looks kind of okay.
It's just,
sorry.
The next step is when you do this now in a time step.
Right.
You have some time step giving on some particular scale that you resolve.
Right.
And then you have this recipe of injecting momenta and energy
right.
into the system. And
right.
so this story is very easy, but it's the nonlinear interaction of what you've done in the last time step with what you're doing now, right? Is the curious thing where I'm wondering whether you would get a solution that looks like the one you're expecting. And so even in the set of Taylor,
yeah,
it's like this very crazy, hard, super narrow shell up front, and there's
yeah, that's true.
Usually the mess there is that we actually can't even get the density jump right in a strongly cooling thing. You don't have enough resolution for that.
Right.
So you already do wrong cooling there because your jump is not high enough, but high enough to trigger cooling. So curious about that aspect now when you sort of then do this time step by time step. The solution that you do set up, is it the one that you're trying to model?
Well, that's a good question. At least for the set of Taylor stuff, you benefit from the fact that you actually know the solution, so you know that you're doing it wrong. Here is not an exact analytic solution. I'm just sort of trying to patch solutions together in a way that I think is reasonable. So it'll be less clear whether, if you try and run this exact simulation and see whether you get this, it'll be less clear whether you're actually getting the right answer or not. And then once you
should be able to do it at 100 different resolutions, essentially.
Well, yeah, that's true. Yeah. Right. As far as once you take this sort of step, next step and try and patch this into a actual larger scale simulation, what the behavior will be and whether that's the right thing or not, that's a good question that I don't have the answer to. I do think that it's a step in the right direction, though, to have some physical idea of what's going on below your resolution so that, I think it's better than what's out there now. Or at least this is the direction we should be going at. I don't know if this specific model is it, but...
it's totally worth trying.
Yeah.
but it's worth it. You'll figure out when you actually
Yeah.
compare it.
Yeah. So you remember at the beginning I was talking about relativity, and I haven't said anything more about relativity. The whole idea was to do relativistic jets, right? So the relativity part is kind of cute, so I wanted to say a few words about that. Thus far, everything has been non-relativistic. So we need to know two things, well, maybe only one thing, about relativistic blast waves. So there is this Blanford and McKee paper where they worked out, the actual solution of the hydro equations in, the relativistic hydro equations, and published this sort of full solution with, not just the position of the shock, but the interior solution. But the only thing that we need is the position of the shock for this guy. So how does that differ? So it differs because here you actually need to know some physics. So if you just want to do dimensional analysis like we did for Sedov-Taylor, then the problem is that now you can make a dimensionless quantity. So you have E over rho T cubed C to the fifth is dimensionless. And the thing that we want to know about is gamma, and we'll talk in terms of gamma squared. So this is dimensionless. We've introduced this scale. What saved us before is that we had no velocity scale. So we were able to we had no freedom in putting together this quantity to make a radius. But now we have a velocity scale, so that's no longer true. So we have this dimensionless quantity. This is raised to some power p, and that's as much as we can do without doing physics. So here you have to, this power p is totally unconstrained until you write down the relativistic hydro equations and solve them, etc. The only thing we need to know now is that for impulsive energy injection where E is constant, this power P is 1. So maybe I'll just write an impulsive. P is equal to 1. And for constant luminosity, P is equal to 1/2. So there's no way to predict that. You can't use dimensional analysis or any other kind of simple thing to get that out. You actually need to, do some physics to find that power. But okay, that part is done. But this is the spherical case. So how would something like this be modified? If you actually have to do a more involved thing and actually do some relativistic hydro just to get the spherical case, what hope do I have of injecting a little relativistic blob of mass and then figuring out what the radius of that is as a function of time? Well, it turns out there's a community of people that have been working on this incredibly, which is that's the GRB people. So here the idea is exactly this, that there's some relativistic pancake of material that's shot out at relativistic velocities. Yep.
So you're now talking about launching ballistic.
Yep.
Whereas before I was more under the impression they were talking about all the mass was being swept
Yeah.
by pointing flux, basically. So are you actually loading the jet with mass, or are you thinking of that, or it's more of a pointing flux that then will pick up stuff?
Yeah. Well, in my mind, it's loaded.
Already loaded.
Yeah, I think, it's already very unloaded. At least that's the case that I was thinking of. So the people that are doing gamma ray burst modeling, you have this, you launch this bit of relativistic material. It's into a small opening angle. And the key thing, which actually makes this easier than you might imagine, is if you ask yourself, okay, before I made this argument that, pressure forces aren't going to accelerate this blob, they're going to cause lateral expansion. But the thing is, when you're doing relativistic hydro, you have time dilation. So this guy, there's some large factor gamma. So the clock of the little blob of material is running slowly. So you can ask whether that's in causal contact with the edge or not. And it turns out if gamma is greater than 1 over theta, the opening angle, it's not. So this actually makes life much, much simpler. So this guy doesn't know that he's only in a little, a focused beam. He thinks he's in a spherical blast wave. So we use exactly the same solution. So the relativistic part is rather easy. You just use the spherical solution. You're taking all that energy and concentrating it into a small solid angle. So your effective energy goes up, but it's exactly the same. Until you get to this point where gamma has dropped to the point where it's smaller than 1 over theta. So in the original gamma ray burst models, sort of circa 2000, early 2000s, the idea was that once this happened, you can compute the expansion time versus the outflow time, and what you find is that the time for the jet to expand is much shorter. So this led to all these models where people were saying, okay, well, it expands to a certain point, and then this condition is no longer satisfied, and then the thing becomes spherical basically instantaneously. So the effective energy that goes into this equation drops suddenly as the thing becomes spherical. But it turns out that people started running simulations. In particular, there was one by Zhang and McFadden in 2009, where when you set this situation up, it turns out that doesn't seem to be the case. So the spreading of the jet is at best logarithmic or very slow, maybe a very slow power law in radius. So what you can, the sort of natural approximation for the level of very crude detail that we're doing this at the moment is just to say that there's no expansion. So the thing stays focused at the same angle until it becomes non-relativistic. And that, I think, is not a terrible approximation. So there you go. So that's the relativistic part. So we're able to take the, basically because of time dilation, and the results of some actual relativistic simulations that were motivated by gamma ray bursts, we're able to just use the spherical solution. So coming back to this diagram, this would look something like the opening angle stays the same. So let's see. So this modifies this diagram at early times, and this velocity it'll be higher velocity. So this, rather than expanding with some non-relativistic velocity, the radius of the shock will basically be expanding with c. So you can patch a little relativistic part onto the beginning if you so desire, and that's not doesn't turn out to be all that complicated actually. So you can, of course, plug in numbers for all this stuff, and of course, you get, for the AGN case, the numbers are sort of well known for the supernova case, but for the AGN case, of course, the energies are higher. It turns out, you get sort of length scales of order kiloparsecs, time scales of order megayears, so it looks kind of interesting for simulation, I think. So, let's see. I think that's it. Yeah, the other thing, I said I worked out some other cases in the paper. So, there are other interesting cases. Like here, I've just done impulsive constant energy injection. You can imagine having constant luminosity. So that is basically a simple modification to this, and I sort of worked that out. But just for the purpose of sketching this now, I didn't want to get into those kinds of details. So, relativistic part, right. So that's it. So just to reiterate, it seems to me, like I said, that this is a more sort of physics-based way to go, compared to what has become standard practice for this kind of thing. I don't know if this specific model is the one. It's certainly not the final word. I don't know if it's the initial word or not. But I think going in this kind of direction is a good direction to go in. And the only thing that I feel like sort of major assumptions are just a bit of, like I said, a bit of energy conservation, a bit of momentum conservation, some dimensional analysis. And then once you get to the relativistic part, you actually need to solve the relativistic hydro equations, but okay, that's been done. And then the last bit is to justify the idea that the jet doesn't spread. And that, it's true, does rely on numerical simulations, but I don't think that that's the sort of most crucial part of this whole thing. So there we go. Thanks for listening.
Actually, for some of the numerical guys that are interested in simulations, that we get together a little bit later today, maybe in 15 minutes or something, and so brainstorm it, what we could do, big computers, code.
Then I'll ask
Black
a
holes.
question from a non-aware. So then if you want to close the loop with what you started with, which kind of this energy, this mass will come out from some of the inflow mass and law budget.
Right.
You have already a prescription for the, with different feedback scenarios, which kind of efficiencies would you use? How much of your initial data goes into that?
Yeah, so let's see. There, I guess, I mean, it's true this doesn't fix the efficiencies. This is just sort of once you decide there's so much energy going in, then I would claim that this is a way to handle it in a way that should be basically resolution independent, or at least less resolution dependent. But it's a good point that you still have to fix these numbers like eta, like your energy efficiency. So yeah, I don't really have guidance on that beyond, I mean, I don't have an opinion about that beyond beyond stuff that's already sort of out there and well known, I guess. It's part of the lore, but
Your jet is heavy. You have problems.
yeah, that's right.
Okay.
So. Oh, so one of the things. So is it true there's no dinner organized for tonight? Has anyone started to do that? Okay. So if people are interested in dinner, there's this place Opal in Santa Barbara. I don't know if people know it and like it or don't like it, but so if people are interested, how about send me an email in like an hour and then I'll. Oh yeah, okay. Means I have to remember my password. Okay, so no, I'll go make a little page right now and then sign up and let's say so it's 3 now.
Yes.
So if people can sign up by like 4, just to have a head count, and then I'll make a reservation. Okay. Thanks again.